This video goes over finding the normal to a plane. So in our first example here, we have a plane and we have a vector equation, and we can sketch those here. So we've got u and v. And what we want to do is use the cross product to find the normal. So we can set that up here. We'll call our first one u and our second one v. So u cross v is going to give us the normal. So I'm going to use the same approach that we did when we learned how to do the mechanics of the cross product, starting with the second component and writing them underneath the vectors. 2, 0, 6, 2. And then I'm going to find the cross product. So again, my first one is 0 times 0 minus 1 times 2, which is going to give me positive 2. My second one, minus 1 times 6, minus 2 times 0. And then finally, 2 times 2 minus 0 times 6, which is going to give me 4. And what I'm going to do is I'm going to factor out a 2. So that's going to leave me with my normal as minus 1, 3, 2. Let's just put this, let's erase the normal here. And then we'll put in that equivalent term here. So I'm going to use 1 minus 3, 2, which is my normal in a direction that is perpendicular to the plane. So now the next part of the example is we're actually going to show that the normal is perpendicular to every vector on the plane. So we have our normal, which is 1 minus 3, 2. And we need to represent every vector on that plane. So let's call that P for every vector on the plane. And we know that it's going to be a combination of the two direction vectors. Varying those parameters, S and T, will give us every possible vector in that plane. So let's write that in terms of a vector with 3 components. So our X component would be 2S plus 6T. Our y component would be 2t, and our z component would be minus s. So now if those two are perpendicular, if we find the dot product, it should equal 0. So I'm going to do 1 minus 3, 2, dotted with 2s plus 6t, 2t minus x. Zoom in a little bit so I have a little bit more space. When I expand that, I'm going to get 2s plus 6t minus 6t minus 2s, which does in fact give me 0. Therefore, the normal is perpendicular to every vector on the plane. Okay, let's look at another example of how we can actually use the normal to generate an equation. So the scalar equation of a plane in R3 is of this form. So this is sort of the different extra part. Our normal is actually the coefficients a, b, and c. So example 5 gives us a point on the plane and the normal to the plane and asks us to determine the Cartesian equation. So the first thing that we're going to do is substitute in our normal for a, b, and c. So minus 1x plus 2y plus 6c plus d equals 0. Now before I substitute in my point, I'm actually going to get rid of this negative sign here at the front by multiplying through by negative 1. So I've got x minus 2y minus 6z minus d is equal to 0. Now I'm going to sub in my point and solve for d. So I'm going to substitute in 1 minus 2 times 2 minus 6 times 2 minus d equals 0. When I rearrange all that, you should end up with d equals minus 15. And that gives me my equation of the plane to be x minus 2y minus 6z minus 15 equals 0 as my Cartesian equation. Okay, that's the easiest information given to find the scalar equation of a plane. This one here is example 6, asks us to determine the Cartesian equation of the plane containing 3 points. So the first thing that we need to do is we need the normal, which means that we're going to have to find AB and AC as direction vectors of the plane. Then we're going to use the cross product. So AB cross AC to find the normal. So the first thing that we need to do is find AB. So that vector gives us 4, 0, minus 1. Then we're going to find AC. That vector should give you minus 1, minus 5, 1. Now we're going to find the normal. So N is equal to AB cross AC. I'm going to use the same approach as before. So starting with my second coordinate, writing everything down underneath, minus 5, 1, minus 1, minus 5. And then I'm going to calculate each part. So when I do this, the cross product is minus 5, minus 3, minus 20. I can't make that any smaller. So I'm going to move on to my second step, which is finding the equation of the plane. And I'm going to start with this format because I have the normal. AX plus BY plus C plus D equals 0. I'm going to substitute in my normal for A, B, and C. Then, as the same thing that I did in example 5, I'm just going to make that first coefficient positive. So 5x plus 3y plus 20z minus d equals 0. And now I'm going to sub in b because it has all positive pieces, but you could substitute in a or c. Doesn't really matter. So I'm going to sub in b, so 5 times 3 plus 3 times 2 plus 20 times 4 minus d equals 0. When I rearrange that, I get d is equal to 101, which gives me my final Cartesian equation of the plane as 5x plus 3y plus 20z minus 101 is equal to 0 as my equation of the plane. Okay, the last thing that you can do is find the distance from a point to a plane. Here you just need this formula. If you're interested, you can send me an email and I can show you where to find the derivation. But here, this is just a plug and chug question. We have a point, which is x1, y1, z1, and we have an equation here. So we've got A, B, C, and D. We're going to take those values and put them into the equation to find the distance. So the numerator is the absolute value of A times x1 plus B times y1 plus C times z1 plus D all over the square root of A squared plus B squared plus C squared. Using a calculator or your brain, this will simplify to 45 over 12. Don't forget to do the absolute value of the numerator. And then we can reduce this to 3.75 units. That would be the perpendicular distance from the line to the plane. Good luck with the homework questions. Hopefully this helps to explain them.